The number of people with diabetes has risen from 108 million in 1980 to 422 million in 2014. In 2016, an estimated 1.6 million deaths were directly caused by diabetes. Another 2.2 million deaths were attributable to high blood glucose in 2012. But why is this happening? First, let's look at what type 2 diabetes is and how it works. Type 2 diabetes is a metabolic disorder influenced by our environment and our genetics. People who have type 2 diabetes experience symptoms such as increased thirst and hunger, frequent urination, fatigue, and an inability to heal and resist infection. But what's happening in the body mechanistically? Well, the food that we eat gives us energy in the form of glucose. To manage this glucose, our bodies produce insulin to help our cells absorb and take up this energy. Type 2 diabetics have resistance to insulin, resulting in glucose not being properly managed and creating a disturbance in our body's homeostasis. The occurrence of diabetes may have an evolutionary explanation. There are currently two hypotheses that aim to explain where type 2 diabetes came from. The first hypothesis was proposed by James Neal in 1960 and is called the thrifty genotype hypothesis. This hypothesis focuses on our ancestral diet. Back when humans were hunter-gatherers, they would go through periods of stuffing themselves with food, followed by long periods of lower food intake, due to food sources being scarce and hard to find. Those who were better able to manage their meals and store them as fat gave them an advantage during periods of famine. These successful individuals were selected for because of their beneficial adaptation and increased fitness, whereas those who didn't have the adaptation were selected against. Fast forward to about 1760. The Industrial Revolution was upon us, bringing about a drastic change to humans' diets and lifestyle. Food was now easier to access and meals were regular and did not require physical exertion. However, food manufacturing also resulted in increased sugars, cholesterol, and other non-desirable components in our food that our ancestors did not have. Though tasty, this was bad for our bodies. Neal proposes that though our cultural environment has evolved drastically, we have not. Our bodies still hold on to the adaptations for periods of famine and storage of glucose that were so beneficial to our ancestors. Once beneficial, these adaptations are now detrimental to our health. Now we consume manufactured food in excess amounts, resulting in significant glucose. However, this was not experienced by our ancestors. This is proposed to be the reason behind poor glucose management, insulin resistance, and therefore type 2 diabetes in some individuals. The second hypothesis was proposed by Barker and Hales in 1992, called the thrifty phenotype hypothesis. As previously explained, our ancestors were exposed to famine and required adaptations to such environments. This hypothesis suggests that the nutritional environment that a fetus experiences in utero has long-term consequences. When a woman is pregnant and is not providing sufficient nutrients, the fetus adapts to its environment and changes its metabolic mechanisms to survive. The baby stores glucose in its system because it is not sure as to when it will receive its next meal. This was a clear, advantageous trait in our ancestors, though in today's society, the environment in which the child grows up may differ in nutrition availability from what the mother was providing. This is then a maladaptive trait because the child's body is unnecessarily storing glucose. Both of these hypotheses point to environmental mismatch. Environmental mismatch is the phenomenon where changes in your environment occur more quickly than your biology can adapt, resulting in a mismatch between your ancestral biology and your current environment, which is what we see with the thrifty phenotype hypothesis, as well as with the thrifty genotype hypothesis. The idea of environmental mismatch in regard to type 2 diabetes has been proven by numerous studies. In 1970, Van Asch and his colleagues found that slow fetal growth in rats resulted in increased risk of insulin resistance later in life. In the 1990s, Barker and his colleagues found the same in humans. Decreased fetal development led to increased metabolic disease risk in adult years. So, where do we go from here? Well, Duncan Thomas proposes that understanding gene by modifiable environment interactions will allow us to develop more effective treatment options and preventative measures. Type 2 diabetes is hereditary, as there is selection for genes that encoded in efficient metabolism and energy fat storage. Though our environment has changed and the selection isn't necessary anymore, the selection still exists. The selection for type 2 diabetes may have been hidden in the population because it was a useful trait before. Now that our diet and exercise has changed, it is a prevalent issue. Due to modern medicine and treatment availability, it likely will not be selected against in populations. Currently, the first step in treating diabetes is to decrease caloric intake and improve diet while increasing level of exercise, thereby mimicking our ancestors' way of life. However, diabetes medications such as metformin may be prescribed to increase your body's tissue sensitivity to insulin, as well as lowering the production of glucose by the liver. If lifestyle changes and medications do not help, insulin may be administered. The biotechnology industry has been working to create new and improved drugs to induce insulin production, as well as more accessible ways of administering medications. A Danish pharmaceutical company called Novo Nordisk is getting ready to release their first oral medication which acts to increase the body's production of insulin while decreasing levels of glucagon. Another exciting area of study is the microbiome. It has recently been discovered that an unbalanced microbiome composition is found in patients with diabetes. A study out of the University of Amsterdam has found that fecal transplants from the gut of a healthy person to one with diabetes can result in short-term improvements of insulin resistance found in obese patients with type 2 diabetes. Diabetes cannot be cured and will most likely remain in the human population indefinitely, as it holds the ability to hide in the population, as not everyone who is predisposed to diabetes develops diabetes. However, with type 2 diabetes, patients are able to go into remission if treatment plans are effective. What can we take away from all this? The big take-home message is that diabetes is influenced by both our environment and our genetics. Following the Industrial Revolution, our environment has changed at a rapid rate. As it takes thousands of generations for adaptations to occur, our biology has not been able to keep up with the rapid changes of our culture, resulting in an environmental mismatch between our biology and our current environment and way of living.